Hello all, welcome to the presentation about FloTorch. To give a brief context about what is FloTorch, it is an open source tool built by Fission Labs in partnership with AWS. And the main agenda of FloTorch is to make sure you can run your RAG experiments at scale with few clicks and within a short time frame. So one of the challenges which we have identified is RAG gives you the flexibility to run run LLMs on your private data in a secure way, but then it involves a lot of parameter tuning and which parameter would uh, resolve in better search results. It's kind of an iterative process, and then enterprises have to spend a lot of person hours in tuning these parameters, running the pipelines, capturing the results, and then tweaking the configuration again, and then go on in cycles until you arrive at the best possible configurations. So to eliminate this and then to make the entire experiments with respect to RAG scalable and then achieve the results in a faster manner, we have built this framework. We are calling it FloTorch. We'll go over the quick demo of how FloTorch works. How we can set up FloTorch will be covered as part of a separate video. So here we are on the home page. We'll get started. So we have a concept called projects. Projects is nothing but for a given data set, for your selected hyperparameters for your RAG experiment, what are the different combinations of experiments that are possible. So a group of these experiments is what we are calling as a project. So we'll go ahead and create a project. You have a project name which can help you identify your project. Right now, we are supporting two regions, US East 1 and US East 2. Please note that while the entire FloTorch infrastructure can be set up anywhere on any region within your AWS account, these regions are where the LLM models would actually be used. For example, we are exclusively supporting AWS at this point of time, and US East 1 and US West 2 are the two areas where we are supporting the AWS Bedrock models or AWS SageMaker instances. So the selection which you are making here is only for the associated LLM services available. The other entire setup can be created on any other account within your AWS, any other region within your AWS account. So I'll select US East 1. Knowledge-based data, this is the data on which you are going to run the RAG experiments. At this point of time, we are just supporting PDF files. We would be using the medical abstract data set, which is widely used for evaluating our entire pipeline. Now the knowledge-based data is already uploaded, let's move on to the ground truth data. So what exactly is the ground truth data? Ground truth data is a JSON file with a number of question and answers provided for us. The way we are going to leverage the ground truth data is, for this knowledge-based data set, we are asking the customers to upload a set of questions on which we can run the entire RAG pipelines against. And then based on the answer provided in this part of the ground truth data, we compare it against the generated answer based on the RAG pipeline so that we can assess how close is our RAG pipeline is. This will kind of help us to generate the metrics such as how accurate is our answer, what is the relevancy of our answer. So to assess these things, we are requesting the ground truth data to be uploaded in a JSON format. It would be a simple JSON format with a question and answer kind of thing. For V1, it is mandatory to upload the ground truth data, but in the future versions, we are actually going to integrate with libraries wherein there is no ground truth data, but then these libraries would take in the knowledge base data set, leverage LLMs, and then generate the ground truth data set. So the idea is just the lack of ground truth data set shouldn't stop our customers from exploring this entire process. For the time being, we'll be uploading the ground truth data set which we have. So now the data strategy part of it is ready. We'll move on to the next step, which is the indexing strategy. So when we say indexing strategy, typically there are two steps involved within a RAG pipeline. One is indexing the data, and the second part is retrieving the data. So when you're indexing the data, what are all the parameters which can affect this indexing process is what we are trying to capture here. If you see here chunking, we are just supporting the fixed chunking at this point of time. So what this does is it takes the entire knowledge base data set, it extracts the text out of the PDF file, and it starts breaking it into fixed chunks. And what would be the chunk size is what is going to be determined as part of this parameter. The typical chunk sizes which are supported are 128, 256, and 512, and these are in terms of tokens, wherein each token would be approximately 4 characters as per the industry standard. The advantage over here is, if you see, these are all multi-select parameters. So say, for example, I want to see what would happen when my chunk size is 128 tokens as well as 256 tokens. So you can generate this multi-select parameters. Towards the end, we will show you what are all the combinations, and then you can select all the combinations which you want and proceed with the experimentation. So now that the chunking strategy is identified, the chunk size is also determined, we want to see what is the chunk overlap percentage. When we take a big text and we are trying to break it into chunks, there might be some information which is overlap between these two chunks. And if a user query relates to that overlapping information, we just don't want to lose context because of this chunking. So that's where we determine this overlap parameter, wherein a little bit of information is overlap between these two chunks, and how much of that is determined with this chunking percentage. So again, everything is a multi-select parameter. So we have defined the chunking related hyperparameters. Now comes the embedding models. At this point of time, we are just supporting Bedrock, and the future scope is going to include SageMaker as well. The idea is to take all the trending Hugging Face embedding models and then support it as part of FloTorch. But for V1, we have limited ourselves to Bedrock. And as part of US East 1 and US West 2, these are the 4 embedding models which are supported. So we're gonna select a couple of them and then move on to the next set of hyperparameter selection. Vector dimensions is what should be your embedding dimension. Most of these models support 1024, with some of them having multiple things. For the sake of this experiment, we are just going to take the 1024 vector dimension. And indexing algorithm is something related to how are these vectors going to be indexed and how are they going to be retrieved. Different algorithms have a different way of optimizing things when it is being indexed. For now, we are just supporting HNSW, which is going to be the default. In the future versions, we will be having more options. So now the indexing strategy is completed. We will move on to the retrieval strategy. So within the retrieval strategy, we have an option to select what sort of prompting do we need. Typically, a zero-shot prompting would be something like we ask a question, the LLM responds with an answer. But then if you provide more and more context to the LLM, the better would be the answers. Let's say, for example, if I say, hey, you are a medical practitioner, you are supposed to take all the information which is provided in the context to you, and then respond only if you find relevant information within the context. Don't respond otherwise. If you give a system prompt like that, and then few set of examples of what was the question and what is the appropriate answer, and then ask the LLM to predict to generate the answer, then there is a better chance of generating an accurate answers. So an example of the prompt file is shown over here. So if you see, this is how it looks. System prompt is what you are instructing the LLM to do. Examples would include what was the example and what was the which the LLM can use as reference to generate the answers, and then final the user prompt. Now that the system prompt is given, the examples are given, what do you want the agent the LLM to do? So having this prompt file and would be helpful in generating more accurate answers. So for the sake of this experiment, we'll take a one-shot prompt, and then we have the JSON file uploaded. KNN is more kind of a nearest neighbor because we are doing a vector embedding. How much of how many hops should it do to get its closest neighbors as part of this vector search is what is determined by this parameter. So we'll select a couple of options over here, and then comes the inferencing LLM. So what would happen typically in the RAG pipeline is you index your data, the user query would come, you would convert that query into the vectors, you would do a vector search and retrieve the relevant context. And then now you pass on the user query, this retrieved information out of vector search, to the inferencing LLM and ask it to generate the answer. So again, over here, we are supporting Bedrock at the moment with SageMaker support coming pretty soon as part of V2. So for Bedrock, we have around 15 models, and we'll take few of these models on which we want to run inferencing. And then the inferencing temperature is how creative you want the LLM to be. Should it just stick to the information which you have provided? Can it use, its own information to generate the answer? So how the responses from the LLM should be is determined by this LLM temperature. So I'm going to select a couple of options here as well. So now that we have completed all the hyperparameter selection, the next step is to get what are the valid experiments. When we say valid experiments, there can be n number of combinations which are possible based on your hyperparameter selection, but not all might not be valid. For example, I selected a chunk size of 512, but a certain embedding model might not support that context, and the max it might support is only 256. Or the embedding model might have a typical vector dimension, but you selected a different vector dimension. So if you consider with this, continue with this invalid combination, there is a possibility that your experiment would fail. So what we are doing after the user make all these selections is trying to see what all would be a valid combinations, and out of all the possible combinations, we are coming back with what are the valid experiments. So what you see here is based on the selections which we have made, the valid experiments that came back from our rules engine. So if you can see, we have all this chunking, vector dimensions, chunk size, overlap percentage. What are all the parameters which you have selected as part of the previous screen, and the additional information of pricing. So what this means is how much would it cost? For you to experiment, and this includes the cost to our LLMs on the Bedrock models, the vector database which is OpenSearch at this point of time, so running that OpenSearch instance, our containers to run these experiments, S3 data cost. So it includes everything, and it kinds of gives you an estimated pricing based on the knowledge based data set which you have uploaded, the runtime which we are considering based on our how long this experiment runs. So considering all these parameters, we are trying to give an estimated pricing so that the users are better informed on when they decide on which experiments to run. So now we have some of these experiments back. So let's take a few of these things. I would try to select, a experiment with a Titan embedding model and inferencing model of Claude with 0.3 as temperature. And then probably I would want to pick something else, some other embedding model. So let me say I select a Cohere embedding with Claude. I want to do Cohere with Meta, and then probably Titan with Mistral. So I can select my combinations. And then once I click on run, so it asks me for confirmation, like, are you sure you want to proceed? These are the models which you have selected. Good to go. So now once I say and click on confirm, the model, the experiments execution started. So this is the screen where you can see all the projects which are, which have been the past projects history or the current running projects, what are their status. So everything related to your projects is found here, which is the dashboard. We have plans to enhance this dashboard to include more information in the future. At this point of time, it shows the name, the status, and when was it created. So let's go and see what is happening within the project. So if you see, these are all the experiments which we have selected. If you can see, there are 4 experiments, and the status says what is happening right now. So if you see here, there is indexing in for a couple of the experiments, indexing is running in parallel. And if you see, there are 2 other experiments which are in progress and which haven't come to the indexing state yet. The reason for this is our system is intelligent to identify what are the experiments with different embedding models so that they can go in parallel, and the experiments which have the same embedding model, for example, the experiment 1 has Cohere embedding glitch and experiment 3 has Cohere embedding glitch. So the system first decided, saw this experiment, and it started the indexing process. And then it saw this experiment, it says, oh, there is another experiment which is already running with the Cohere embeddings. So you wait in the line, and as soon as that is done, you can start the execution. And the reason for that is Bedrock at this point of time has rate limiting. We want to make sure that we are not hitting the Bedrock service and then running into rate limiting errors. So we kind of made the system configurable so that in case of Bedrock throughput increases, or if you have provision thing, you can configure n number of experiments to run in parallel. At this point of time, it is set to 1. So as you can see, the retrieval process has started as well. The indexing has been completed. Then comes the retrieval part. So it goes, it evaluates all the questions. It tries to generate the answers for those set of questions. And as soon as the retrieval process is done, you would start the evaluation process, which is to compare the ground truth data and the generated answers, and then generate the metrics. As you can see here, the evaluation process has begun. We are using Raga's library to do the evaluation. In future, we are trying to add more evaluation libraries like LLM as a judge feature, which is provided for Bedrock. We are also evaluating few other libraries. So we are planning to incorporate these other systems and make sure that the evaluation process is more robust, giving you more insight so that you know which is the best pipeline to go for. One another thing to note is this page is a live indicator. It keeps refreshing so it keeps on polling to see what is this experiment status, and it kind of auto refreshes and shows what is happening and what is the current status of that experiment. Once the evaluation progress is completed, you will see the metrics over here, like what is the faithfulness, the context precision, the aspect critic, and the answer relevancies, along with the pricing and the duration, like how long that experiment has run. So these all metrics would give the users information to compare the experiment, not just with respect to the accuracy of the responses, but also at what cost and what time is that experiment able to generate those metrics. Now you have different parameters for you to assess an experiment from different dimensions, and based on that, you would be able to make a better intelligent or more understanding decision of which pipeline do you want to take it into production. So as you can see here, this process completion, this process has been completed, and you can see that the metrics for this particular experiment has been returned, uh, which is with the relevant metrics, and then how much was the duration for that entire experiment ran. And as well, you can see that the other two experiments have started the indexing process, and then one of them went into retrieval. And once the retrieval is completed, it will go into the evaluation. So while the other experiments are running, we'll go and see what are the other things which you would get once the experiment has been completed. So if you click on this experiment ID, you can see that there are the questions which are the ground truth questions which have been uploaded by the user, and then these are the generated these are the ground truth answers, and this is the generated answers. So you can tweak the system prompt to generate more information or less information, but this is how the system has generated the answers which you can compare against. And there is also option for you to download the results so that you can go into that results page and then do further analysis. So uh, So the other experiment has been is running the evaluation, and then once the evaluation is completed, the other two experiments evaluation would also run. And once all the experiments are done, the project status will move on to completed. We can see now that all the experiments have been completed. And if you want to fetch the results, you can go into that particular experiment and then download the results from there. Once all the experiments have been completed, the project overall status is marked as completed. Now we are good to go ahead and create another project with a different set of data, different set of hyperparameters, and select a new set of experiments and start your execution. That is all we have as part of B1. We have active enhancements which are happening to this part and going to be addressed as part of B2. Please follow this space for more updates. Thank you.